Hi there. So far we've been accumulating different tools in order to be able to analyze the convergence of, say, the Jacobi and the Gauss-Seidel method in a similar way that you would have done with your root finding. Of course, things are more complicated because we're dealing with vectors and matrices now rather than scalar quantities as you did in root finding. So the one thing we need to be able to do now is be able to determine the length or the size of a vector and the size of a matrix. And this is called norms and is the exact analog of absolute value in scalar quantities. Okay. So all along we're looking at Jacobi and Gauss-Seidel, and we're looking at algorithms of the form xn plus 1 equals c vector minus b of x of n. And we're asking the question ultimately is what are the conditions on B, and by implication A, so we can show that we've shown in the previous two videos that we can derive a B from A by decomposing it for convergence, and that given that many numerical algorithms, and by the way, many of these numerical algorithms form the basis of the newly popular data science area as well, involve AX equals B. This is a very important question. So we've done the first stage of this is by expressing B in terms of L, U, and D. That's been the first stage. Before we can proceed though to a proof of convergence for Jacobi, we need to do a little bit further work, and that involves norms. That's what we'll be doing today. So we need to be able to quantify the size, if you like, of vectors and matrices. So when we've done convergence analysis for root finding before, so we're looking for the analog of the modulus for scalars. So we did a convergence analysis, say, of the fixed point method, and we used the modulus of the error. Now we need to find the equivalent. What's the equivalent of modulus for vectors and matrices? So here is where we use norms. And once we've got this in place, then we can proceed with our convergence analysis. So this, as I said, this is a derivation that's over several videos. We're sort of building up tools as we go along, but it will be worth it in the end, because then we'll be really able to do convergence analysis of actually quite a complicated matrix problem. So consider, so this is norms now. We just have an x, and we're going to have all the components, x1, x2, all the way up to xn. What is the size or geometrically the length of x? And it turns out there's more than one answer to this. More than one answer. And in these in the lecture notes, I give 3 types. In the videos here, I'm just going to go through 2, the sort of 2 key ones for moving further on. So what we're going to say first is the Euclidean or L2 norm. This has notation of 2 bars and a subscript 2. So again, it's borrowing from your sort of absolute value with scalars, but now we're adding another bar there, and we're putting the subscript 2. And that would do that of the vector x. And that is basically summing over all components the squared so this is Pythagoras theorem applied to n components. So it's an n-dimensional Pythagoras theorem, if you like. We basically sum the squares of all the lengths. So if n is 2, you recover your Pythagoras theorem. We'll show some examples. Again, so just to sum the squares and then we square root. And that probably geometrically is the most intuitive, certainly in 2 dimensions. But it turns out that maybe that's not the most useful one because of this squaring and summing and then square rooting. That can be a little bit more cumbersome algebraically when we come to proving convergence. And there's other methods that involve it. I'll just mention in passing the Manhattan norm. I'm not going to go into too much any detail about this because this is not used in the any further, but see lecture notes for if you're interested about that. The third one is very relevant, and it's the infinity norm. L infinity, or sometimes called supremum. Norm sup. And it's at this point that maybe we just impinge a little bit with the notation that gets used in pure mathematics analysis. Okay, when you're looking at sequence and you're wanting to prove convergence. So there's here we at least use the same concept about the maximum, and I need to use the next board for that. So the L infinity is notated norm of our vector nan is again our 2 vertical bars x, but it's now got a subscript infinity, and the computation of this is a little bit simpler, and this is why it's popular. Basically, it involves taking the absolute value of each component from I to 1 to n. So basically take the absolute value of each component of x and go and find its maximum over all the components. And this is simpler to compute or manipulate than L2. I mean, the analogous thing so far in the course, if you remember back to where we did the convergence of the bisection method, we didn't actually compute the absolute error, we computed the maximum absolute error, and that turned out to be sufficient to prove convergence. In a similar way, we're looking at the maximum absolute values of all our components, and that sometimes is sufficient to prove convergence. We don't necessarily have to square them and then subsequently square root them. Okay, so the main two things are L2 and L infinity. So what I want to show is just show you some examples of how these are computed. So let's keep an eye on the time there. Examples of L2 and L infinity. So we'll just define a vector now, a 3-component vector, 2, -3, and 6, and then we just need to apply these different rules. So L2 is notated like this. Remember there, that is the sum of the squares of all the components square rooted, Pythagoras. So first component is 4 square, second component is 9, third component 36. And I've set it up nicely that that's a square number. Square root of 49, which equals 7. So that's our L2 norm for this vector. Our infinity in contrast is the maximum of all the absolute values. So maximum absolute 2, maximum absolute 3, maximum absolute -3, which is also 3, maximum absolute 6. And of course the maximum here, those values, is simply 6. So different answers, but as long as you use your norm consistently in your proof, i.e. you use, if you're going to use infinity norms, you use infinity norms throughout, that's okay. Or if you use L2 norms. But as I say, L2 norms is the one that's probably you've come across before. Pythagoras, well, definitely you come across Pythagoras before. Otherwise you wouldn't be mathematicians. And it makes most geometric sense initially. The L infinity norm is going to be the one we're going to use throughout, and that's what it is for this vector. So the next thing to show you is how we can use this for convergence. So let's use norms in a, shall we say, a simple convergence example. So now we're going to change from a fixed vector to one that's a function of n. So we have a vector now which is a function of n. So a sequence of vectors, which is exactly what we're doing with our Jacobi method, yeah? So we're starting with an initial vector and we're going stage by stage until we converge to the a solution. So let's just consider an artificial or a simple example, which is it's got components that are 1 over n, 1 plus 1 over n squared. So I'm writing this in row format, but then I'm just going to put a transpose here to put into column format. So this is deliberately set up that it's simple. We can see that this is going to converge as n tends to infinity, because 1 over n goes to 0 and 1 over n squared goes to 0. So we know that xn tends to x star, or if you like, a true solution, and that is equal to 0, 1, 0 transpose as n tends to infinity. Okay, so what we're going to do is then, because we've got the true solution, we're going to then define our error. Let's call it e to the n, which is x of n minus x of star. Okay, that's our error at any stage. So it's simply that each component taken away from here. So when we do that, if we take xn minus x star, it's just going to be the n components that remain. So that implies E of n equals 1 over n squared 0. But of course we need to we want to see that the error goes to 0, which when it was a scalar was no problem, we just had the one component, but here we have multiple components, so it's not an unambiguous statement to just say the vector goes to 0, because we can't see that. We need to really take the norm. So now take the our infinity norm. So this is analogous to taking the modulus in your scalar error in your previous. So I would encourage you to have a look back to some of the proofs we did for root finding, error convergence, particularly for, say, fixed point method, and see the analogies here now with the Jacobi method. I referred to the beginning that actually the Jacobi method is a vector form of fixed point method, so the analogies are worth exploiting here. So now we take the infinity norm, so we take the infinity norm of our error, so which is that's just the maximum of the absolute value, so that's just the maximum of 1 over n squared and 0. Okay, at any one point the maximum of these two quantities, 1 over n squared, is simply 1 over n. So now we've got an unambiguous statement because of our norms of whether this vector converges or not. So within the framework of the infinity norm, we know that the error, the size of the error, if you like, is 1 over n. And now it's very simple. I try not to use the term trivial too much. Things are only trivial when you understand them, hey? But anyway, trivial when you understand it. So the error goes to 0 as n tends to infinity. Equally, we could use the L2 norm for this one. So we could do the 2 norm of this quantity, which is simply adding the squares. So then that's 1 over n squared plus 1 over n for square rooted. And also we could clarify that goes to 0 as n tends to infinity. And this is algebraically straightforward for this problem, but when we have more complicated problems, the 2 norm may be not so useful. So as the infinity norm. Okay. Okay, but so that's how we deal with the size. That's how we quantify the size norm, I'm using those exchangeably here, of a vector. But how do we do the equivalent for a matrix? And I'll leave you with that cliffhanger, if you call it that. Got to try and introduce some excitement here for next time. Basically, we want to use, the quick answer is, we want to use this same idea about going through the components of a vector, whether it's finding the maximum absolute value, or so we basically want to try and reduce say a 2 by 2 matrix down to a vector first, and then use the same algorithm for as a norm. So that's the principle, but we'll explain that next time. Okay, see you then. for